Hey guys, and welcome to another A-Level Further Maths revision video. Today we're taking a look at Further Stats 1 and we're going to do some exam revisions. So just using this official textbook here for Edexcel, we're going to take a look at some exam questions. So, question 1 here, we're taking a look at the mixed exercise 1, so the very first chapter in the textbook, and we're taking a look at discrete random variables here. So we're given this probability function and we have basically two parts, when x is 0 or 1 or when x is 2 or 3. So the first part is asks us to show that k is equal to a quarter. So this is pretty standard. This is something you should probably expect to see a lot with these kind of questions, showing that k is equal to a value. And how do we do that? Well, we know that the sum of the probabilities should be equal to 1, right? So all I need to do here is consider setting up my table and then equating all the probabilities and then putting it equal to 1. So let's demonstrate that. Let's see what that looks like. So I can set up my table. So there's 4 values that x can take. So they are 0, 1. So that's my line 1, 2, and 3. Okay. So make sure yours is a bit neater than mine. Mine's a little bit scruffy, but yeah. So 0, 1, 2, and 3. And then we need to consider what the probabilities are. So the probability that x is equal to little x. So how do we get that probability? Well, let's just consider what happens when x is 0, for example. So that's k times 1 minus 0, so it's k times 1, so just k, right? Let's consider what happens when x is 1. So 1 minus 1 is 0, so instantly that one will be 0. The next one, so when x is 2, so that means we've got to work with the second probability here, the second function. So 2 minus 1 is 1, times it by k, we get k again. And then when x is 3, 3 minus 1 is 2, times it by k, we get 2k. Okay, so that's our table there of our probabilities. Now, remember, the sum of these probabilities is equal to 1. Okay, so the sum of the probabilities is equal to 1. Okay, so all I've got to do now is add up these and then set them equal to 1. So k plus 2k is equal to 1. Just adding these up, setting it equal to 1, and then solving for k. So that's 4k equals 1. So therefore k, nice and easy, just has to be a quarter there. So that's our very first part of the question done, just working out the value of k. So part B again, pretty standard, finding the expectation of x and the expectation of x squared. So if I just clear all this, remember that we have k equals a quarter. In fact, we don't even need to, we're given that, so that's the nice bit of this question. So e of x, how do we do that? Well, remember, the expectation of x we obtain by timesing our table together. So what I mean by that is, I probably should have actually kept it. So we had 0, k, we had 1 and 0, we had 2 and k, and we had 3 and 2k. So to get the expectation of x, all I do here is I times my x here by my probability. So 0 times k, just 0, right? 1 times 0, again 0. 2 times k, so that'll give us 2k, is the expectation of x, so that's 2k, and then 3 times 2k gives us 6k there. Now we can add these together, so that gives us 8k, but we can actually work out what this is, right? Because we know that k is a quarter. Okay, so using the fact that k is a quarter, and we know the expectation of x is 8k, we can work this out. This is 8 times a quarter, and this works out nicely as just being 2. Okay, so that's what we should expect to find for the expectation. And then the expectation of x squared, again, the method's just the same, but instead of it being x, I'm going to square these values here. Okay, so the first two again will just be 0, because 0 squared is, is 0 anyway. That would be 1 squared times 0, so them two instantly we can just kind of get rid of. So now I need to do 2 squared, so 2 squared, so this is the next part here. This is for e of x squared. So that's 2 squared times k. And then we add on 3 squared, which is 9 times 2k. So that's 4 times k, so 4k plus 18k there. Okay, we can just do like we did with the expectation, add these together, and then we can actually work it out. So that's 22k. We know that k is a quarter, so this is 22 times 1 over 4. And then we can just simplify this. So you can just put this on your calculator, or you can just simplify it by hand. So that's 22 over 4, so that'd be 11 over 2. And then obviously 11 over 2 is just 5.5. Like we was required to show. So there we go. So that's the expectation of x squared. Good stuff. And then finally we've got to find the variance of 2x minus 2 here. Okay. So this is one of those questions that looks kind of harder than it actually is. And the reason for that is the mathematics isn't particularly tricky. You just got to remember your formula. So I just clear all this. Let's have a go at it. So the formula that you really need to remember here is the variance. So the variance of x, well, that's going to be equal to the expectation of x squared, which is quite kind of give you the expectation of x squared minus e of x squared. Okay. They give you e of x squared, so even if you really struggle to work it out in the question, you could use that. So as long as you could get e of x, you could do this question still. E of x, we work that out as being 2, so that's minus 2 squared. So that's 5.5 minus 4, so that gives us 1.5 there. Okay, so that's a 5, 1.5. But we want the variance of 2x minus 2, so that's the variance of x. So how do we work out now the variance of 2x minus 2? Well, it's a lot simpler than you think. All we do is we take the coefficient of this 2 here to the front of the variance, so this is 2 lots now, squared. You just need to square this value. So if it was 3, it'd be 3 squared, 4 squared, for example. Because it's 2, just 2 squared, times by the variance of x, and that's it. This minus 2 here doesn't have an effect on it, okay? It's just the coefficient of the x here that actually has an impact on the variance now. So all I'm doing here is 4 times the variance of x, which we've just worked out being 1.5, so 4 times 1.5, which works out nicely as being 6 there. Okay, so 4 marks for that question. That, you know, if I was to get that on my exam, I think that's quite a nice question to get. Very often, this would be kind of like the first or second question on your exam. Not always, but very often. So yeah, so you should kind of expect that to be, you know, some of your easier marks there. But there we go. So that's that question done. Next question here, we're taking a look at kind of like the power and the size of a significance test. So the first 2 questions are very standard kind of like textbook definition questions. So this is just something that I would recommend learning, whether it be through flashcards, if you've got bad memory like I do, or whichever method you find effective for kind of memorizing definitions. So a type 1 error. Well, a type 1 error is just simply when you reject H0, but we should have accepted H0, but you should accept H0. But you should accept H0. So what I'd recommend doing is just learning one of the errors. You can either learn the type 1 or the type 2 error, and then the other one's just kind of the opposite, right? So what I'd do is I'd just learn the type 1 error. That's when you reject H0, but you should have accepted H0. And then type 2 is just kind of the inverse of that. Okay, there we go. So that's literally all you need to say there for your 1 mark. For part B, the size of a significance test. Again, just a very standard textbook question in terms of definition. So the size of a significance test is just the probability here. So the size of a significance test is just the probability of basically rejecting the null hypothesis when it's true. So kind of like our part A here. So it's a probability, can't write and talk, probability of rejecting the null hypothesis. So I mean null hypothesis is your H naught. When you should accept. Okay. And we can actually give a definition for this. So the size then is just equal to the probability of making a type 1 error. Because like I said, this is just essentially here, your part A. So this is why they kind of go together. Like so. Okay. And then we're going to use this information now to work out part C. Okay. So let's clear all this so we've got some room to have a go with it. So part C here wants us to find the size of the test. So the first thing we're told is that it's a single observation on a random variable x, where x is distributed with a normal distribution here with mean, mu, and the variance here is 10. Okay. So the hypotheses here are h naught is mu equals 20 and h1 mu is greater than 20. Okay. And then they tell us the critical region, so I'll call it CR, that's x greater than or equal to 25. So, remember, the size of the test is the probability of making a type 1 error. And the probability of making a type 1 error is when you reject H0 when you should have accepted. So how do we reject this? Well, we need x to be greater than or equal to 25. So what we're looking for here is the size is equal to the probability of type 1 error, which is the probability that x is greater than or equal to 25. That means we're in the critical region there when mu is 20. That's what we're testing, right? Our hypothesis. Mu is equal to 20 or is greater than 20. So mu equals 20. So now this is just a standard probability here using the normal distribution, so just your standard A-level stats. So this is going to be 1 minus now the probability that x is less than 25 here. So make sure you get your inequalities the right way around. Sorry, I should put that mu is equal to 20 here. So we're given that mu is 20. So just plug this in on your your graphical calculator if you've got it. If you don't, you'll have to work out by hand. What you should get here when you do 1 minus the probability is that your final answer is 0.0569 there. So this bit here, you just need to put it into your calculator using the NCD function. And you should get this probability here. So that's that question done. 4 marks there. Quite a lot around for just 4 marks, but there we go, get it done. Next question is exercise 2F. So this question we're looking at kind of the Poisson distribution and the binomial. So let's take a look at what we've got. So x is distributed with a binomial distribution with n being 5, and our probability is just p, we don't know what it is. We're given a bit of information. We're told that the probability that x is greater than or equal to 1 is 0.83193. So the first part just asks us to work out the value of p. So how would we do that? Well, you've got to be confident with how these probabilities work. So remember, if we're looking for the probability that x is greater than or equal to 1, we do this, or we calculate this doing 1 minus the probability of x being less than or equal to 0. Like so, okay, so it's 1 less than what we're working with. Sorry, so this should, well, it would actually be x less than or equal to 0, but because we're at 0, then that just means we're going to find it when x is equal to 0 here, okay? So that's kind of the beauty of this question, because we can work this out exact now. So this is going to be 1 minus, and what I'm going to do here now is I'm going to apply my formula to work out the probability that x is equal to 0. So that'll be 5 choose 0, so 5 choose 0, times p to 0 of 1 minus p to the 5. Well, this here is just 1, p to 0 is 1, So what I actually get left with here now is 1 minus p all to the 5. But we know this now is equal to our probability that x is greater than or equal to 1. 0.83193. Okay. So at this point here now, all we need to do is just start solving this. So the first thing I can do is I can take this here onto this side, and then take my minus 1 minus p to the 5 onto that side. So doing that, I'm going to get 1 minus p to the 5 is equal to 0.16807. Now I can take the fifth root of both sides. So doing so gives us 1 minus p. Obviously take the fifth root of that, you just get 1 minus p. Do the other side on your calculator, and what you should get is 0.7, so it works out very nice. 0.7, and then just solve this here, so therefore p must be 0.3. Okay, so that works out very nice. If you really, really want to, you can do it by trial and error, but I definitely would not recommend it. The questions usually aren't written to where it's something that you would do, so definitely just use your formulas together. So just be very careful for that fact here. So it would normally be less than or equal to this here minus 1, but because 1 less than that is 0, we just work out the exact term there for x equals 0. Okay, so I'll probably lay 0.3. So now, nice easy follow up here. We can now work out the expectation and the variance here. So e of x, well, how do we work out e of x? Well, e of x, nice and easy, it's just n p. So n times p, well, n is 5, p is 0.3, so 5 times 0.3, or 30% of 5, what would we get? We just get 1.5 there. So that's a nice easy follow up, that's one of the marks, and then the second mark for the variance of x. Again, just another formula, standard question here. It's going to be np times 1 minus p here. Well, np we've already done, that's 1.5, times 1 minus p, and p is 0.3, so 1 minus 0.3 here. So 1.5 times 0.7, and what does that simplify to? What does it actually give us? Well, that just gives us 1.05. So if you can get your part A there, part B is a real nice easy question, but definitely a couple of tricky parts in that part A. But yeah, there we go, that's the full question done. Next question here is another kind of binomial and Poisson question. This time here, we're kind of looking at approximations. So if we have our distribution here, where n is 150 and p is 0.02, can we work this out? Well, the probability x equals 3. Honestly guys, just do the part on your calculator. And this is why I always recommend a graphical calculator, because you're allowed to do it and you'll save yourself so much time. You can do the method if you really want, but the graphical calculator is absolutely fine and you do get your marks for it. So put this on your calculator, and what you'll get here is 0.226. Okay? If you don't have a graphical calculator, you just do it like we did for the very last question, but instead of it being x equals 0, you'd use your 3 here, okay, and just slightly alter your formula. But that's probably that you should get, 0.226. Then for part B, we're told that a Poisson random variable is used to approximate x. So we want to write down the value of lambda. So how do we do this? Well, remember, we obtain lambda as the mean, and the mean of a binomial is just n times p, right? So all I need to do is apply that to ours. So lambda is equal to 150 times 0.02. Plug this on your calculator, or work it out top of your head if you really want, and you'll get 3. So lambda is equal to 3. But now the question is whether this Poisson approximation can be justified. So you've just got to be confident with kind of the conditions of why this approximation works. And there's 2 conditions that this holds under. So, looking at ours, we have a large n. So we have a large n, so that's 150. So statistically, we define that as being quite large. So we have a large n, 150. That's my first point. We also have, So the only other kind of information you can't use here is your probability. So we also have a small probability. So a small p, so that's 0.02 or 2%. So therefore what we would say is, because both of the conditions are satisfied here for our approximation, the approximation is justified. Okay, so then are just the two conditions you're kind of looking at, a large n and then a small p. And that wraps that question up, so quite a nice easy one, a pretty short one there. So the next question, probability generating functions, usually one of the harder topics for a lot of students. Let's take a look at what we've got here. So question 12. So we've got two parts. Part A just wants us to find the value of k, and then part B wants us to actually find the probability of that probability generating function. Well, for part A, again, kind of like your discrete random variables, this is a very standard type of question. But be confident these aren't particularly tricky, or the part A isn't particularly tricky. All we've got to do here is be aware of the fact that if you sub t equals 1 in, then the probability generating function should be equal to 1. So what I mean by that is, subbing in 1 means the full probability generating function will be equal to 1. So how does that work? Well, we have our probability generating function there. So I sub 1 in, so that's k times 3 plus 2 times 1, because t is 1. So we're saying t equals 1, so 2 times 1 is 2, plus t squared, so 1 squared, which is 1. This expression squared will be equal to 1. Okay, and like you see, it's pretty much kind of like the exact kind of same style for the discrete random variables. So simplify this now. 3 plus 2 is 5, plus 1, 6. Square that, that's 36. So we've got 36k is equal to 1. So therefore, nice and easy again, k must be equal to 1 divided by 36. So that's the first part. And the next part is a little bit tricky, or a little bit trickier. It's still quite a nice probability generating function compared to some of the trickier ones, but you've got to be careful with some of the maths. And this is usually where people kind of forget the method for it. For this one here, if I just want to find the probability that x equals 1, we can actually just obtain that by expanding our probability generating function and then finding the coefficient of the t. Because we only want x equals 1, it'll be the coefficient of t. If it was x equals 2, it'll be the coefficient of t squared. So let's expand this. So it's 1 over 36, 3 plus 2t, plus t squared, times 3 plus 2t, plus t squared here. Okay, so we need to expand these brackets here, so it's going to be quite long. I'll do it down at the bottom here. So this is 1 over 36 times, so 3 times 3, that's 9. 3 times 2t, so 6t. 3 times t squared plus 3t squared. So you can expand this in whichever way you find comfortable. So I'm just expanding as I go along. 6t again. 4t squared. 2t cubed. And then finally t squared times 3, so 3t squared. T squared times 2t, so 2t cubed. And then finally t squared times t squared, we get t to the 4. Okay, so there's a lot of terms there. So I'm going to take this all the way up to the top now, just to finish it. So this is still 1 over 36. I've already simplified everything by hand anyway before doing the actual question here. But just double check it yourself, guys. Make sure you simplify all this. So hopefully you should get the same as me. So you should get 9 plus 12t plus 10t squared plus 4t cubed plus t to the 4. Okay, so I kind of run over a little bit there, but you can see. I mean, the rest of it you don't need. We only need this 12t here. So remember, we said we're checking the coefficient of t. So that's 12, but obviously that's not a probability. You know, your probability should be smaller than 1. And the reason for that is because we're timing it by 1 over 36. So 1 over 36 times 12, so that gives us 12 over 36. So therefore, the probability that x equals 1 is equal to 12 over 36, which we can simplify very nicely to 1 over 3. So there we have it. So that's that question done. Yeah, definitely a trickier topic in the textbook, but you know, I quite enjoy it as a topic. And then finally, moving on to the very last question here, we have a hypothesis testing question. So we're working with a Poisson distribution here, looking at a rate of 39 vehicles per hour. So that's how we know it's Poisson, because we're looking at a certain time frame. So as soon as you see the word kind of like per hour or per time interval, you know you're working with a Poisson distribution. So that's the first thing, just recognizing the distribution. But we're actually looking for a 10-minute interval, so just be very careful how you set up lambda here. So A and B. Well, if it's in a 10-minute interval and it's 39 per hour, so 39 per hour, obviously a 10-minute interval, we divide this by 6 because there's 6 10-minute intervals per hour. So 39 divided by 6, that'll give us per 10 minutes, right? So if you do this on your calculator, you'll get 6.5 here. So therefore, what we're saying is that X is a Poisson distribution with lambda 6.5. Okay, so we've got the information now. We know what distribution it is. Now we can just work it out as we go along. So part A, the probability that exactly 6 cars pass this point. Part A and B, actually, just use your calculator. Again, you don't have to actually show the actual working. You know, just do the calculator. So probability that X equals 6. Do it on your calculator. You should get 0.157. Okay. So you'd be using Poisson PPD for that one. Okay, because it's an exact value here, equal to 6. So part B, is it part B? Yeah, part B. Can't speak. At least 8 cars. So this is where it gets a little bit trickier. Just got to be careful with the language here. So if we want at least 8 cars, the very smallest value we should expect is 8, right? Because we want at least 8. So as a probability, this is X is greater than or equal to 8. That's the very smallest value. So, like we were saying before, we do 1 minus this probability, but we subtract 1 off it. So this is X less than or equal to 7. And again, just plug this into your calculator. This time it Poisson and then PCD, okay, because it's less than or equal. So do this on your calculator. What you should get is 1 minus 0.673, and that's applied to 0.327 there. So there we have it, set them our two probabilities, so 0.327 and 0.157. And then finally for part C, we're actually performing the hypothesis test now. So if I erase all this ink, let's have a go with it. So it's a 5% level of significance for this test. So like any hypothesis test here, always state our hypothesis at the beginning. So H0 and H1. So because it's a Poisson distribution, our parameter will be lambda here, and again lambda here. So what we're actually testing, so they've introduced a new one-way system, and it's suggested that the number of vehicles passing this point has decreased. So that's the very kind of significant bit of information that it's decreased. So we know our H1, our alternate hypothesis here, will be less than. This will be equals to. So now, using that information, what's this value going to be? Well, again, they're doing a 10-minute interval. So, comparing it to our previous 10-minute interval, what we should expect is that this is equal to 6.5. And what we should expect to find is that it's less than 6.5. If it has decreased, that is. Okay, we will find that out in a minute. But that's what we'd expect, right? So it's going to be less than 6.5, or it'll be the same. So, we're given a bit of evidence here. So during a randomly selected 10-minute interval, 2 vehicles pass. So we need to work out that probability here of the Poisson distribution. The question is, how do you kind of choose your inequality? Well, so again, X is distributed by Poisson, 6.5. So how do I choose that inequality? Well, if we're testing that there's less than 6.5 here, we match the test to it. So we're going to check now for less than or equal here, 6.5. Okay, less than or equal to 6. Sorry, not less than or equal to 6.5, less than or equal to 2. Okay. So inequality is the right way, and to make sure you get the right number, do not do what I've just done. So doing this on your calculator, this just works out nicely as 0.0430. So that's what we call our test statistic. And we compare this now to our significance level. So significance level, which is 0.05. Okay. Because for one-tailed test, we don't need to half this or anything. We just keep it as 0.05. So what we do now is we compare our test statistic to our significance level, and then that gives us the conclusion. We either accept H0 or we reject H0. So our test statistic is less than it because it's 0.0430, which is less than 0.05. So as a result, because this is smaller than the significance level, we reject H0. Okay, so that's our conclusion. So reject H0, and then we can give it a little bit of context. So what we're expecting here is that the mean number of vehicles so the mean number of vehicles passing at a given point, or the given point, passing at the given point has decreased. So hopefully you can read this. My writing's terrible at the moment. Has decreased. And there we have it. Okay, so 4 marks for that last bit of that question for our hypothesis test. So I really hope this video has helped, guys. So that brings us to the end of the video and the end of the questions. I've got plenty of other further stats 1 revision videos on the actual specific topics. So for example, discrete random variables, probability generating functions. So be sure to check them out if you want some more revision. Any issues or anything like that, please leave a comment below. Cheers, guys.